with the collaboration of Richard Willey from Newcastle. This representation is about using wall blowing in order to reduce the drag of a turbulent boundary layer and the associated net energy by the help of Bayesian optimization. So we can't emphasize enough the importance of reducing the skin friction drag of an aircraft, for example, where 50% of the drag comes from skin friction. And 50% of that skin friction come from flat surfaces like the fuselage, where we expect having a zero pressure gradient. This is why we are interested in a zero pressure gradient turbulent boundary layer and reducing the skin friction of that turbulent flow. So there are many techniques to reduce skin friction of turbulent flow. One of them is wall blowing. So if we have a permeable surface or micro-perforated plate and we apply a pressure on one side, then the flow will go through that surface perpendicular to it. And we can reduce the drag significantly by over 80% or 90%. So there are key features of this kind of control that distinguish it from other techniques. It works. It has a very simple design. It can reduce the drag significantly, over 80% or 90%, using a small blowing flow rate. The velocity comes from the wall is less than 1% of the free stream velocity. And also it works for subsonic, supersonic flows. It's even beneficial to apply at high Reynolds number. So it suits real life applications. Another key feature here for the blowing, if we look at this example here for thermal boundary layer, if we apply the blowing in this region, then we see a significant drop in the skin friction drag over through the whole control region. But after the control region, we still have this significant drag reduction that lasts for very long distance downstream. There are two main disadvantages here for this thing, for this control type. The one is this wall roughness can increase the skin friction drag. But there are many studies that show that optimizing the holes and the plate thickness can introduce a plate that's hydraulically smooth. So this is not an issue anymore. The other thing is the high energy expenditure of the control. So the idea here, which is the focus of our work, is instead of applying the blowing everywhere in the boundary layer, what we can apply intermittently. So apply the blowing here, then wait, apply, wait, apply. So we can make use of this bonus drag reduction that happens after each blowing region. So we try to optimize this distribution of the blowing at intensity using. Oh, yeah. So I opened the wrong one. Okay. Anyway, so yeah, we're trying to do the optimization for this one using the Bayesian optimization to find the parameters of the flowing. The way Bayesian optimization works is using a Gaussian process, where if we have an available point here, or if we're trying to find the objective function of this curve here, which is quite at this point, then we can select an arbitrary point and calculate the actual objective function of this one, and use this available data to calculate the Gaussian mean and the uncertainty or the covariance. Now we have the uncertainty and the mean. Now we have two options. The first one is to go and explore the highest uncertainty region, or to go and select a point where we expect to have the lowest minimum based on this red curve here. So we have this trade-off between both, and doing this trade-off, we can go to the next point. Using these 2 points, we repeat the process where we do the Gaussian process again and get the mean, get a new uncertainty, and doing the trade-off between uncertainty and the mean, we get a third point here. And we keep iterating until we reduce the uncertainty up to an acceptable level. And now we have a good fit of the true objective function using the Gaussian mean. And now we know for some confidence that, okay, this is the location of the objective function, the lowest mean. The good thing about Bayesian optimization, it works with, it can find the global minima with few iterations, and it works with non-convex and noisy objective function. So we started at this point near the local minima, but we managed to find the global minima, which is here. So this work has two sides. The first one is to calculate the skin friction of the table boundary layer using the numerical simulation. And the other one is to calculate how much power we need for the blow. So for the first one, we're using compact 3D that solves incompressible Navier-Stokes equation using sixth order compact finite difference scheme with same implicit time advancement. And thanks to the 2D decomposition and the MPI, this flow solver is very efficient in supercomputers up to thousands of cores. So we have two studies. The first one using DNS, the other one for low Reynolds number, and the other one is ILES for higher Reynolds number. So for the DNS, this is our computational domain. We're having a laminar boundary layer at the inlet here with tripping to transit the boundary layer from laminar to turbulent. And we can reach Reynolds number based on the boundary layer momentum thickness up to 2,200. We apply the control or the blowing as a boundary condition where we have no slip boundary condition everywhere apart from the control region where the wall normal velocity equal to whatever value we put. This region is located between Reynolds number 470 till 700. So inside this control region, we can divide it into sections as intermittent waves, like this one. And the number of waves inside this control region is the NB, number of blowing patches. And we also have the duty cycle that defines the length of the active region to the length of the non-active region. And we have the CB, which is the intensity of the blowing, the ratio between the wall normal velocity to the V-stream velocity. So we have three parameters to optimize using Bayesian optimization. And our objective function is to find the net energy saving. What we mean by the net energy is the sum of the power that we need to sustain the flow or to overcome the skin friction of the turbulent boundary layer, plus the power that we need to apply the control or to introduce the blowing in the boundary layer. So the first one, the pumping power, we get it from numerical simulation. The first one, we get it from experimental measurements. So now we have an accurate representation of what we would get in experimental or real life application using experimental measurements. So this is our blowing device where we have this speaker. It's covered by micro-perforated plate, and by the movement of the diaphragm of the speaker, it pushes the flow through the holes of this plate. So now we can measure the power between the power input to this speaker against the velocity that comes out from the speaker. And we have different results for different frequency of the speaker. Using this curve, the most efficient one, we use it to calculate the power input to the speaker or the power required for the blowing or the control. Now we have all the parameters that we need for the Bayesian optimization. We have the skin friction. We have the input power for the speaker. We have the parameters. Now we run the Bayesian optimization for the DNS case. We find, okay, the best option for us for this setup is to use uniform blowing with a turbulence intensity 0.5% of the stream velocity. We can achieve 52% of drag reduction and 1.2% of net energy saving. So we published these results in this paper, Physical Review Fluid, last year. So we have two questions here. The first one is why the power saving is low, 1%. And the answer is we apply this control at low Reynolds number, and we're expecting if we apply this control to high Reynolds number, we improve the efficiency and we can have higher net energy saving. The other question is why intermittent blowing is not a good option here. Answer could be because we have a small control region. If we divide it into patches, the length of the control region will be small and the flow will not adapt enough to give us this bonus drag reduction that we have downstream. So we decided to go to high Reynolds number and try to increase the length of the control region. So to do the large Reynolds number boundary layer, we used implicit large eddy simulation, which was introduced by Limbley, where the numerical dissipation can be controlled in a way that mimics the spectral vanishing viscosity. So this is the spectral viscosity that we add implicitly to the flow, the red curves, and the black curve is the one the explicit spectral vanishing viscosity from the literature. They are quite similar. We apply the spectral vanishing viscosity to the higher wave numbers. So thanks to the ILES, now we can double our grid size and the time step. For the ILS, the cost for the same domain size is 7% of the DNS cost. And we validated our grid and the LAS against the DNS using 3 cases, the canonical case and 2 blowing cases, one with high intensity and one low intensity and high intensity. And there is a good agreement in the skin friction drag and in the velocity, the velocity profiles as well. Now we can go to the high Reynolds number. This is our domain with the same boundary condition as the DNS, but now we can reach Reynolds number as high as 4,300. It's twice as we had in the DNS, and also the control region expands between 500 and 1,300, which is almost 4 times as long as the DNS. We followed again the same procedure for the Bayesian optimization, and now we have 24 iterations. This is the summary of all the iterations that we did with the Bayesian optimization. We have 24 iterations, and we found that at iteration number 20, we can achieve net energy saving over 3%. That can be done using intermittent blowing, where we have 10 blowing batches inside the control region, and blowing intensity 0.7% with duty cycle 90%. And that can achieve also 82% maximum drag reduction locally. On the other hand, if we apply uniform blowing with intensity of 1%, then we can reduce the drag by 95%. And in that case, we gonna pay extra energy as low as 2%. And this is a very interesting situation in case if someone wants to increase the speed of the vehicle or an aircraft without paying much, for example, without like using an afterburner in a jet fighter, for example, then you can like use wall blowing to reduce the whole drag. So, okay. So looking at the skin friction of these 2 cases, very interesting. So the red one, the one with the maximum drag reduction, we have significant drag reduction here, up to 95% drag reduction at this point. And when the skin friction tries to recover, it doesn't recover to the canonical value. It stays, we still have this significant drag reduction downstream. Similarly, in the case with the maximum net energy saving, the blue curve, you can see these spikes. These spikes corresponds to the location of the non-active region between each blowing batch. So the good thing, they don't recover to their canonical values, and also we still get this bonus drag reduction downstream. So the combination of both, we can improve the efficiency of the whole controlling process and get some net energy saving. So looking at some flow visualization for the DNS case, with one with the canonical case, this one, and one with the high intensity flowing, one with low intensity flowing. In spite of achieving high drag reduction in the control region, surprisingly, the turbulence density over this region increases dramatically. That may surprise some of you. So this is why we looked at, we like to investigate more why this is the case and why we have drag reduction in this region and downstream. So we looked at the FIK identity, and also we are looking at the POD decomposition. But here I'm presenting only the FIK identity. So for the FIK identity, decompose the skin friction into 4 components. The first one is the Reynolds number thickness contribution, the Reynolds number stress contribution, mean convection contribution, and the spatial development contribution. So we calculated all these quantities in the control region and downstream of the control region, and took the mean. And this is what we have. So we have the canonical case, the low Reynolds number, the low intensity flowing, high intensity flowing. The left side is the one for the control region, and the right side is the one downstream of the control region. The main contributors here in the boundary layer is the spatial development, the Reynolds stresses, and the mean convection. So over the control region, as you can see here, the spatial development increases significantly and the resonance also increases. But to get a drag reduction in the control region, the mean convection has to drop dramatically. So the reason for having drag reduction in the control region is reducing the mean convection. Totally the opposite mechanism appears in downstream. So downstream, the mean convection contribution increases, even it can shift the sign if we are a bit aggressive with blowing. And the spatial development has to drop to achieve drag reduction. So downstream, the drag reduction mechanism is the spatial development. So totally different and opposite drag reduction mechanism upstream and downstream. So to conclude my work, so we use Bayesian optimization that can converge quickly. So with a few iterations, we managed to find an acceptable drag reduction, and we confident that this is a convergent one. The other one, we applied a realistic estimation of the blowing power using experimental results. And with that, we found that it's possible to achieve drag reduction as high as 3% with significant, we managed to achieve net energy saving as high as 3% and drag reduction as high as over 85%. And also it's good to know that the wall blowing becomes more efficient when we apply it at higher Reynolds number. So we imagine if we take this study, we apply it at much higher Reynolds number, probably these results are going to improve. And that's good for real life application. For future work, we're doing some POD for further analysis of the flow. And thanks.
Thank you very much, Omar, for your presentation. Is there any question? If there's any question, please raise your hand and I will ask you to talk. Okay, looks like there is no question. Everyone is very shy. I have a question, Omar. I mean, you didn't explain the difference between the local maximum drag reduction and you have something in your table called GDR. So can you explain what is GDR?
Oh, okay. Okay, so the local maximum drag reduction is if we go all along the line here and we try to pick the maximum drag reduction. Technically, it's somewhere here for this case. But the global drag reduction that we refer to this one, so for this case, it's around 35%, and for this case, it's 25%, is the average of the whole drag reduction from the starting of the blowing up to the end of the domain. So it's in the average of the whole drag reduction in this, almost in the whole domain.
Okay, thank you. Vishal, you have a question.
Hi, I just was curious about when you go from DNS to implicit ILES, were you able to make big changes in the wall region, or the main changes in the grid were in the outer region only?
Okay, so for this current ILES study, I tried to keep the wall resolution as close as possible to the DNS because I want to have a well-resolved boundary layer, especially if we apply the control at boundary layer. So I don't want to miss any significant structures here. But we did some study using a channel flow where we have the first point of the boundary layer, the first point in the grid is over y plus equal 5, and we managed to capture most of the velocity profiles, the kinetic energy. So, but for this one, yeah, I tried to make it as close as possible to the DNS, especially near the wall, like.
Okay.
Thank you.
Thank you. Nikos, you have a question?
Yes. Hi. Hi, Omar. Nice presentation.
Yeah, thank you.
Thank you. Can I ask, close to the outlet of the domain, the skin friction has not yet reduced to the levels that it was without control.
Yes.
So you would say that this is kind of the comparison you are making is kind of unfair to your control strategy, because this would persist downstream, further downstream.
Yes.
Okay.
Yeah, actually,
the percentages are going to be higher.
Yes, exactly.
Okay. Okay.
Yeah, but we know that this is going to be higher, but yeah, this is what we have, and we can't.
I understand. Just wanted to.
Yeah.
Yeah.
I just want to point out, I mean, for the DNS study, the computational domain was long enough to recover the canonical skin friction coefficient, but it was because the control was very small. So we managed to recover the skin friction coefficient. For the LES, because the control domain is 4 times bigger, the effect of the blowing can be felt further downstream, and the computational domain is indeed not long enough to recover the canonical value. So it's very promising indeed that it's probably a little bit unfair for the numbers that we have at the moment. But yeah, it would be nice to be able to increase the size of the computational domain in the X direction, but that will require Archer 2, for example.
Okay, thank you.
Yeah, thank you.
Paul, you have a question?
Yeah, I was just wondering, in your table, does it give any indication of whether you can actually make things, well, how robust is the improvement? So, okay, so actually now that I've got a chance to look at it, I was just wondering, does the control system need to very finely keep things balanced, or can it easily tip into energy loss? Okay, thanks for showing the table again. That's kind of cleared that up. I was just wondering how sensitive it would be.
Okay. Yeah. Yeah, it's quite. Yeah, it's a bit sensitive, but yeah.
I'm afraid we will have to stop here. Thank you, Omar, again for your nice presentation. And I'm going to ask Paolo to share his screen once Omar.
Yes.
If you, yes, Paolo.
Can I go?
Yeah, you can share your screen. Thank you.
Right.
So while you are sharing your screen, Paolo, I'm going to introduce you. So Paolo is working at the University of Sheffield with Pierre Rico, and it's also going to be a talk about drag reduction for wall bonding turbulent flow, but this time it's going to be a passive control strategy in a channel. So Paolo, please. You have 15 minutes and try to stick to 15 minutes. Thank you.
Okay, can I go? Can you see my screen?
Yes, everything is fine.
Okay. So thank you very much for the introduction, and good afternoon to everyone. I am Paolo Olivucci from University of Sheffield, and I would like to present some data today about we obtained in the context of simulating passively rotating disks in channel flow, and with the aim to study them for drag reduction. So a brief outline here. This work is concerned with the numerical study of simulation, DNS, in channels of these devices. These devices are essentially a disk which is fitted on in a cavity on the wall. So there's the fluid flow. This is the solid wall, and this is our solid disk. It's a cross section, and we'll explain a bit more later, expand a bit later on this. This is actually our setup, and we will first review the modeling of the system and how we are going to couple the disk dynamics to the numerical simulation of the flow. And there we're going to analyze, we're going to share some results on the passive oscillations of disks like this under a turbulent flow. And we also consider a second configuration, which is we call half disks, where essentially the same device is used. However, half of it is sheltered, and so it's prevented to interact with the mean shear and with improvement and performance. Right. So let's review device modeling first. So this again is the cross section of our disk. So the disk is mounted in this cavity. It's supported by a bearing, and it's a certain diameter, and it's only free to rotate about its central axis. And therefore, its dynamics is described by a simple 1 degree of freedom rotation, where we have the disk angular velocity. We will actually be concerned with studying the disk edge velocity, which is more commonly, which is more significant for drag reduction purposes, and with more meaningful. And so we considered three torques acting on this disk. The first is TF, which is the torque generated by the turbulent shear stress on the flow-facing surface of the disk, expressed by this integral where xc is the center of the disk, and tau is the shear stress, instantaneous shear stress distribution. And then we have TH. TH is the housing torque, which is generated by the flow occurring in the cavity, which is filled with fluid. And we will expand in the next slide on this. And then we have minor losses. The more important one is the bearing, obviously has some friction, but is orders of magnitude in all cases considered smaller than the housing flow, which is the most important source of friction. The disk has an inertia. The disk inertia is proportional to the disk, the solid density. Sorry, just trying to. Okay. I'm not sure you can see this, but geez. So it's proportional to
see it, but we can't see the last line.
Right. Okay. Yeah. Okay. Exactly. Okay. Trying to.
You just
all right. So rho S. Yeah. Okay. Rho S is density of the material the disk is made of, so proportional to the inertia. Therefore, here again we show the device. We show the our channel, and we also show a disk of several sizes fitted to it. We will simulate the disk of increasing size, and the parameters of the system are obviously the Reynolds number of the flow, the density ratio, so the density of the solid disk to the density of the flow of the fluid, and then the cavity aspect ratio, so the cavity depth dh to the disk diameter, which determines the nature of the flow in the cavity, and the relative size of the disk to the channel half height. We will fix some of the parameters. We mostly vary the disk dimension, disk size. However, we choose some choices have to be made. For example, the density ratio, we fix it at 2.7. This is an important choice because such a low ratio allows the time scale of the disk oscillations to be short enough to provide good statistical convergence and to not produce overly long simulations. This is actually inspired by the practical case of considering an aluminium device in water. which is 2.7 times heavier than water. Aluminium is 2.7 times. If that was air, for example, that would be almost 1,000 times as large, and therefore the time scale of the disk oscillation would be much slower. And last modeling bit. So the housing torque is not simulated. So the flow underneath the disk in the cavity is not simulated. So what we actually simulate is just a plain channel. Instead it's just modeled by this, by a linear Couette type flow. So it's essentially a linear azimuthal velocity profile. And this is its associated torque, which is linear in the angular velocity of the disk. And this flow regime holds. We verify that this flow regime actually holds for the cases, the flow cases we present. We'll present the next slide. And so this model essentially is experimentally and from literature, experimentally and theoretically proven. Now we set out the model. So this is a view of our system at a glance. So essentially, this is a passive device. The only source of input power is the pressure gradient, which is linked to the fluid flow. It generates the shear stress distribution that integrates on this surface, gives our torque. The torque is plugged into the disk dynamics that produces the angular velocity, which then generates distribution of a velocity distribution on the wall, which is then fed back as a boundary condition in the Navier-Stokes equation. Now we see some results here from several simulation we did for increasing diameter. We have 3 diameters here. This is the fluid torque measured on the disk surface. As you can see, it's an increasing function. So its variance increases with the diameter. So bigger disks are subject to strong forces. And the disk edge velocity instead decreases. This is the same view, but here we show the same simulation, but more simulations, 11 in total. And we show that the fluid torque increases with the variance of the torque. The mean is 0. Increases about a power less than 2 with this diameter, and the disk edge velocity decreases with slightly more than -1/2. This is another view to understand what's happening on the wall. So this is our fluid torque on the upper surface that can be decomposed into the streamwise shear stress contribution and spanwise shear stress contributions. And these are a color map of these two terms. Essentially, you multiply the streamwise and spanwise shear stress by the moment r. So further you go from this center, the stronger the contribution to the torque is. Obviously, the long-term average is 0. So what actually happens is that the oscillations are given by strong streaks at the very edge, at the further edge of disks. And the streamwise shear stress is about 2 orders of magnitude, contributes 2 orders of magnitude more than spanwise to the torque. We have also an animation to see what happens. So this is essentially our simulation we run. And as you can see here, we see the streamwise velocity gradient streaks, and the blue arrow shows the torque acting on the disk. And we can notice that when the torque is very strong, for example, what is that? Oh, sorry. For example, here, right here. What happens here is that we have a very strong streak on the edge of the disk, and all the rest basically averages out. Instead, yeah, so that was the idea behind it. We can also construct models linearizing the system to get the gain function of the disk, but these are more sophisticated and need a linearization of the system. But this can help us to understand the response, the velocity response of the disk to the shear, to the turbulent torque, to the fluid torque. And the disk responds strongly to more strongly to low frequencies than high frequencies, which is so basically a low pass filter. We are now going to briefly review half disk configuration. So the half disk configuration is essentially uses the same actuator. This is our new, so it's laid out in an array. It must be pointed out that this configuration was subjected to experiments, has been investigated experimentally by Koch and Kudurovich in 2013 in the turbulent bundle layer, showing a streamwise slip velocity of up to 2.5 friction velocities, a retail 500, and a drag reduction of up to 70% on the disk. Here we will consider a simplified proof of concept numerical experiments in the channel retail 180, using the same device model as before, where the housing torque produced here is augmented by 50%, ideally consider the fluid flow in these under the solid shelter, which is not modeled. So again, it's a plane channel. The results are encouraging. We tried essentially here we tried different configuration where the varied disk diameter and the cavity depth to decrease or increase the frictional torque, the frictional housing torque. And for some configuration, we notice that turbulence intensity and Reynolds stresses are strongly attenuated directly above the disk. And the disks do rotate on the action of the mean shear up to a slip velocity of about 1 friction velocity on the exposed surface. So these are some of the results. These are two best cases. Here we find a map of the local drag reduction. And we can see that the drag reduction distribution is inhomogeneous. We have a very strong drag reduction here on the exposed half of the disk, and on the rest of the wall, there are regions of drag increase, especially downstream, so it's or regions where the drag is not altered significantly. These are some of our results. This is the diameter. So we tried, for example, two different diameters and different cavity depths. And this is the best case. The last line of the table is the best case, where a drag reduction on the whole wall drag reduction we find is about 5%. Whereas if we limit ourselves, as did in the experiments, on the exposed half of the disk, the drag reduction is almost 14%. So these results are encouraging. However, in the sense that prove that this configuration might achieve drag reduction, but several points have to be further researched. For example, investigating the entire Reynolds number range of the original experiments, which goes from about 200 to 500. And also, it's important to elucidate the parametric dependence of the local drag reduction, because we have seen that we have regions of high drag reduction and a region of drag increase, and which might be also linked to the limitation of the simplified boundary condition adopted as compared to the real world case where actually a solid shelter was added. Thank you, and if you have any questions, I'll be happy to discuss them with you. Thank you.
Thank you very much, Paolo. Are there any questions? Well, I have some.
Okay.
I'm going to start as I can't see any raised hand. My first question is, I wanted to know a little bit more about the experiments and what level of drag reductions was obtained. I know it's a slightly higher Reynolds number than your study, yes. But what type of drag reductions are they observing in the experiments, and is it comparable to what you are getting in your simulation?
So the drag reduction they observe is generally comparable in that their Reynolds number range is from 200 to 250 to 500, and instead our simulation is at 180.
Yeah.
And the drag reduction values, they range from 11% to 17%. And instead we observe as measured on the exposed surface. We measure a drag reduction of almost 14%. However, it must be said that these values are obtained for a different. So in this table, what happens is that in the last two lines, so the first two lines are two different disks with the same diameter, but two different diameters, but at the same. The cavity depth underneath the disk is the same. Instead, the last two lines, the cavity depth is increased. Why is that increased? Because that's for lowering to decrease the friction of the fluids underneath the disk. When that is done, then the disks spin faster and a high drag reduction is obtained. So we do obtain artificially a drag reduction that is larger than the experiments.
Okay.
Obviously the Reynolds number is different, so it might be.
Yeah, and I have one last quick question. What's the rationale of doing half disk as opposed to
half disk? The rationale is that half disks introduce a slip velocity of the wall. So this is the slip velocity we obtain on the disk surface, and therefore this introducing slip velocity of the disk is a well-known drag reduction paradigm that here we are trying to achieve through these passive devices. And there are many other methods in the literature to achieve, proposed to achieve slip velocity, among which hydrophobic surfaces, which are obviously a more complex technique. The goal is to obtain a slip velocity drag reduction paradigm. Yes.
Great. Thank you very much again, Paolo. We need to move on to the next talk. Well, I think Stefano has a question about the efficiency of the device at a higher Reynolds number. I think this will be answered in the next few months when you're going to investigate higher Reynolds number.
Yes.
Thank you.
Thank you.
If you can stop sharing your screen, Paolo, and then
sure.
I'm going to ask Jae-Wook to share his screen.
Yes, I am sharing my screen now.
Fantastic. So the next presentation is from Southampton by Jae-Wook Kim, and this is a work in collaboration with some colleagues in Germany and in South Korea, and it has to do with channel flow with large longitudinal ribs. So please go ahead.
Thank you, Sylvan. Thank you for inviting me to UKTC online talk today. My name is Jae-Wook Kim from University of Southampton. This is a kind of work in progress of a work that I am working with three other academics from three different countries. So this is part of a paper, working paper that all of us are working on. This is on large longitudinal ribs. Ian Castro is the leading author, Alex Stroh from Karlsruhe, and Hee-Chang Lim from Busan National University of South Korea. So probably I am the least qualified person amongst the authors to present this work because my main research area is on aeroacoustics, but this is a good opportunity for me to learn about channel flow and wall turbulence. So let me briefly introduce to you what the simulation condition is. So it's a channel flow with a half height where on the bottom of the wall there are large longitudinal ribs. So this is a kind of schematic that you are seeing here. So some of the important key parameters here are capital H, which is a half channel height, and lowercase h is the height of the rib, which is in this case about 10% also of the channel half height, and W is the width of the rib, and S is the basically period in span of the ribs. So for typical DNS, the domain size was set to about 8 times the h in the streamwise direction, and 4 times h in the spanwise direction. So there are multiple ribs included in the computational domain. There are obviously previous works. There are experimental work and also numerical work. So this is a relatively new research area, started from Van der Waal and Ganapathy Subramani in 2015. There are a few groups who are working on this particular subject. One of the things that I would like to introduce is that based on Huang and Lee's DNS result published in 2018, you can see that the secondary flow formations show that the flow is mainly coming down in between two ribs, and flow is coming up from the center of the ribs. So those are sort of common features that were found from both experimental and numerical studies. So in this current work, we are looking at some new feature, new findings that haven't been covered in the previous work. One of them is critical points in the secondary flows, and also Spanwise-averaged velocities and stresses, looking at them in more detail. And the previous work covered some of the various cases, for example, different spacings between two successive ribs, and also the aspect ratio of the ribs, and also the shape of the ribs, and so on, and with different Reynolds numbers as well. But we haven't found a study about the effect of the ratio between the channel height versus the spacing between the ribs. So we are going to briefly talk about it. And also we are looking into describing the log-low regions when there are longitudinal ribs. So I'm going to present our investigations on log-low as well. So these are the data sets coming from 3 different groups in addition to existing work by Van der Waal et al. And Huang and Lee. So we are looking at various cases, various geometric and flow conditions. VS denotes work from Alex Stroh from Karlsruhe, and KC denotes the work from Southampton. LC denotes work from South Korea. So there are 3 different DNS codes that were used for this work, but let me briefly introduce the code that was used from Southampton, supported by UKTC. So the code that was used from Southampton's work was named Canard, based on 4th and 6th order wave number optimized compact finite difference method and filters, based on pentadiagonal and 7-point stencil formations. And 4th order Rajkota time matching scheme was used. The code is showing about 97% scalability on 10,000 or more cores. And this is particular simulation case that you are looking at. RE tau was about 550. This is compressible code. So the Mach number needs to be set. The Mach number was at a lower subsonic case, 0.25, to minimize compressibility effect while having a reasonably good numerical efficiency. So as I said, the computational domain was sufficiently large to avoid any blockage effects and so on. So this particular simulation case was based on about 115 million cell count distributed over 13,680 cores in Archer. About 3.3 million Rajkota iterations were spent for having 80 flow-throughs in 19.6 work clock hours in Archer. So we had three simulations of this kind from Southampton. So as I mentioned earlier, we were looking at some secondary flow features. This is time averaged, Spanwise-averaged, and also rip period averaged contour plot and the velocity vectors you're looking at here. So one of the things that we are interested in is what the flow features look like, especially near the rip area, because particularly in experiments, the PIV couldn't reach the flow field very close or under the rip height. So we are looking into these flow features in more details. I have denoted a saddle point with a red circle and nodal point with blue rectangles here. So the outer nodal points are well-known features, but the other three here close to the rip wasn't very clear in the past. If you look at this, because I first commented about this upward moving velocity components also found in Huang and Lee's DNS. Now, if you look at closely, then there is a saddle point, and velocity is actually coming down towards the rip, very close to the rip area due to these rotational secondary flow generated around these top of the rib areas. So these are the things that aren't made clear in the past. And we also looked at some critical points, looking at the entire field now from bottom to top. There are quite a few critical points we identified, or in addition to those that we just saw, a number of nodal points as well as saddle points, half saddle points as well. So this is for the first time we identify these critical points, and that is in line with the Cont et al.'s rule, that is summation of the nodal points and half nodal points and saddle points and so on will give you a value of 0. So that was confirmed in this work. And we looked at the effect of the height relative to the rib spacings. So keep the rib spacing the same, we increase the height, and as the height increased, the upper part of the boundary layer showed quite different changes. However, the height about the same size of S, which is the rib spacing, and below the mid to low boundary layer region show very little change. So that is quite consistent behavior in the lower half of the channel flow that we identified. But as you could see, the flow features below the rib height has got very complex features. So we are going to look at them in more detail in the future. So looking at the spanwise average stresses. So you're looking at various cases here. This is the axial normal stress. This is vertical, sorry, this is spanwise, this is vertical. Apart from very high Reynolds number case denoted by green curves, most of them are in a good agreement in terms of the trend there, because they are in the region of RE tau 500. And there are two things that I want to comment. The first thing is that the curve stress profiles deviate quite significantly from the smooth channel. So dashed green line is Hoyes and Jimenez smooth channel DNS. As you can see, the around the rib height, which is 1 here in the vertical axis, and about up to 2, twice the channel, the rib height, the deviation is noticeable. It's very significant deviation from the smooth channel, whereas higher than that, 2 times the rib height, then the agreement with the smooth channel is restored. Apart from the very high Reynolds number case and the blue curve, which is RE tau equals 500, but that case was made based on very small domain size, so that wasn't producing the same trend. The next one is axial velocity profiles in different spanwise positions. So we took 7 different positions. So from 0, 1, 2 to 6 here, there are different spanwise positions, and these are the axial velocity profiles. Normalized, the first one, bottom left corner, is the curves of axial velocity normalized by the local U tau. Local U tau means the U tau calculated at each spanwise location separately. As you can see, the agreement is the curves collapse very well in the sublayer region, whereas there are deviations in the top of the boundary layer, because obviously the local U-toe is working very well with the near wall region, whereas the curves, particularly very close to the side of the rib, number 4 is the closest point to the side edge of the rib, has got a very significant deviation from the others, which is quite natural anyway. Whereas if you normalize these curves by the global U-toe, which is the Spanwise-averaged U-toe, which is denoted by the dotted, solid dotted black line here. If you normalize by that, then the sublayer near wall region does not collapse very well, but the outer region collapse well. So you can maybe think about some blending of this U-toe value from the local to the global as you go from the wall to the top. So that is here. So if I use that sort of blending approach, then the agreement, the collapsing is generally much better across the entire domain. However, the number 4, which is the closest one to the side wall, is still odd one out, which is making, obviously it's not agreeing with the others. Spanwise U plus profiles, the Spanwise-averaged one. So what we are looking at is for different cases, there are different U plus profiles. However, the log-low region seems to be in a consistent value here. However, what I'm showing here with the black dashed line is the conventional log-low. So all of them are actually sitting below the conventional log-low. So initially we thought about kind of energy loss, so that the axial velocity is reduced, so that the lateral and vertical velocity components are more promoted. However, we found that the vertical and spanwise velocity components are two orders of magnitude smaller. So that didn't explain this deficit of axial velocity or axial energy of the connecting energy of the flow. So that was the kind of dilemma. So this is a kind of common observation in the previous work as well. So that was kind of a problem that we wanted to explain, and carefully thinking about the situation where the cross-section of the ripped channel is obviously different to a plane channel, and also the wettest surface on the wall area is different to smooth wall. So if the pressure gradient is the same between smooth wall and ripped walls, then the U-toe values need to be different. However, if you plot the classical log law in the same plot with the ripped channel cases, then they are not the fair comparison, because the log law should be normalized by the U-toe of the ripped channel. So we implemented the correction factor based on the geometry and so on. So applying this correction factor to the classical log law, so the modified log law is derived. And as you can see here, the orange curves are the modified log law. Now the modified log law curves are matching much better with our ripped channel cases. So it was not kind of a loss of axial velocity, it's just a kind of mismatching scaling of the log law that we found. So that was fixed, I think. And also we applied the same principle to the boundary layer case, because Huang and Lee's DNS and also Van der Waals cases were boundary layer cases rather than channel case. So we also apply this modified log law to the boundary layer to match much better in the loop region with the Huang and Lee's curve. So that was a good outcome, I think we achieved. So in summary, we have covered those items. The future might be a closer look at the secondary or maybe tertiary flows around the junctions and corners of the ribs. And we are planning to look at more unsteady features based on wave number frequency analysis. And we are planning to explore higher Reynolds numbers beyond 500. And also we are going to look at some various different geometries as well. So thank you for your attention.
Thank you very much. That was a very interesting talk. Sadly, we have very few minutes or seconds, I will say, for questions. I don't see any raised hand, but I wanted to ask you very briefly, did you try to do a code-to-code comparison with exactly the same setup, the same Reynolds number, same boundary conditions and stuff? Because
Yes.
Okay.
So basically KC4A and VS4 are very similar. So same geometry. The only difference is the small difference in Reynolds numbers. So we have compared, for example, in the stress field here. So the yellow one and yellow with circle and the red one with triangle. They are the counterpart with the same conditions and geometry and flow. So we found that they are in very good agreement with each other.
Okay. Yes. Okay. Well, thank you very much. We need to move on to the last talk. So I'm going to ask Yvonne if you can share her screen. And so the next talk is from the University of Warwick. Is going to be given by Yvonne Chen, and this is work with her supervisor, Yvonne Chen. And this is about turbulent pipe flow and uniform momentum zone. So please, Yvonne, go ahead. I think you need to unmute yourself as well.
Okay, could you hear me?
Yes, so you will have to speak a little bit louder if you can.
Got the full screen on a second. Okay, so our talk today is about on uniform momentum zones in a turbulent pipe flow. So this is a DNS study of a fully developed incompressible turbulent pipe flow. The solver used is NAC 5000, which uses spectral element methods. The periodic boundary condition is applied in the pipe axial direction. In this study, we use X, R, and theta to denote the streamwise radial and azimuthal direction of the pipe, and the total streamwise velocity is in capital letter. We performed 4 Reynolds numbers for this pipe. The higher 3 from ITAL 300 to 1000 were performed on Archer. The chord of the mesh is shown below for ITAL 500 and 1000. The results shown later will be only for ITAL 500 only. So a little background on the uniform momentum zones. In wall-bounded flows, channel, pipe, and turbulent boundary layer, the velocities are remarkably constant in large regions, like these ones and the ones highlighted in blue. And the velocity jump abruptly across some thin shear layers, internal shear layers, like these ones and these ones highlighted in magenta. So these regions are called uniform momentum zones, and The internal shear layers bounding them are the zone interface. So along the interface, there are clustered vortices as marked in this figure. So the vortex cores are mainly at the location where the shear layer rolls up. In this particular snapshot, there are 3 uniform momentum zones from the wall. So they are zone 1, 2, and 3. So each traveling with relatively constant velocity and therefore will contribute to 3 distinct peaks, each representing 1 zone. And the higher peak means the zone is larger. So in our study, we follow this technique to detect the uniform momentum zones using the histogram of the streamwise velocity. So for each snapshot, a histogram is computed using the vectors in the 3D subdomain with a streamwise window size of 0.2 pipe radius. In this example, the histogram shows 3 peaks at 3 modal velocities. And so it means we have 3 uniform momentum zones bounded by 2 interfaces. So the interfaces at the dashed lines are defined as the minimum being between each 2 peaks. And the interface is traveling at velocity denoted as U kappa. And the interface as isosurface of U kappa are the black contour lines on the right-hand side figure. So in 3D subdomain, this interface looks like this. So in 1/3 of the pipe length, the interface is unwrapped below. So the red color, the red streaks are the sweeping of high-speed fluid towards the wall, and the blue color indicates ejections of low-speed fluid up away from the wall. So, and the top view of our 3D interface on the left is therefore very similar to the velocity contour drawn at the average wall location of the interface on the right-hand side. So away from the wall, this is the large-scale motions with significant meandering behavior. The interface closer to the wall, in the other hand, reveals the near-wall activities. So much closer to the wall, the streaks become very refined and in much smaller scales. So the histogram-based detection for uniform momentum zones is performed in all, from all 3D snapshots over time for a collection of instantaneous zones. The figure on the left is a PDF of the average number of zones locally, which is 5 in average. So all these instantaneous zones are then grouped into 6 groups according to the velocity they are traveling at. So group 1 in blue has the fastest traveling zones, and group 6 in yellow has the slowest zones, which are naturally very close to the wall. This is a PDF of the number of zones that fell in each modal velocity group. We can see group 2 have most of the zones traveling about 90 to 100% of centerline velocity. And the zones in group 1 traveling above the centerline velocity is much less than group 2. And for zones traveling below 60% of the centerline velocity in yellow is very rare. So the statistics of the zones and their interfaces are investigated by group averaging. So first we look at the contortion of the zone interface. We measure the 3-dimensional contortion of the interface by measuring the ratio of the surface area of the contorted interface in the red color to the area of a smooth reference tube with no contortion. So the tube's radius is the average radius of the contorted interface it's compared with. The interface is less contorted near the wall in the last group. So starting from this group, the contortion of the interface grows exponentially towards the pipe center, and it's almost more than 10 times more contorted than its reference tube's area. So the increase in the interface contortion with distance from the wall indicates the increase in the meander of the large scale motions from the wall to the center, and from small scale near the wall to large scale in the pipe center. We computed the ensemble average around the zone interface as function of the distance from the interface. So we take the average in the white area surrounding the interface with 20% of the pipe radius on each side. And here we introduce Kc as a distance from the interface. So Kc equals 0 at the dashed lines here are virtually the interface. And on the left-hand side, when Kc is negative, is from the interface towards the pipe wall. And on the right-hand side, one can see it's positive. It means from the interface to the pipe center line. And the left figure is a group average streamwise velocity for 4 groups. So the signature of the uniform momentum zone interface is this step-like velocity jump across the interface, whereas the velocity is quite constant on both sides of it. The figure on the right-hand side is the corresponding velocity gradient. So the peaked velocity gradient at the interface show more clearly the abruptness of this velocity change. So the velocity jump at the interface is increasingly larger and steeper for interfaces residing closer to the wall in group 4 in magenta. And this is the group average azimuthal vorticity omega theta. So away from the interface, the vorticity is very constant. And for groups closer to the wall, they will naturally have stronger vorticity to begin with. So the vorticity peaks slightly before crossing the interface from the wall and remain very low inside towards the pipe center. So this peak vorticity near the interface is plotted on the right-hand side, along with the velocity gradient. So we can see from the pipe center on this side, there's a log linear increase in the vorticity and velocity gradient to the wall area. So far we know that the zone interface is very contorted and velocity gradients and azimuthal vorticity peaks at the interface. So we further look into the evolution of the interface with the change of local vertical structures. So these two instantaneous interfaces are from the same snapshots, but the background contour and azimuthal vorticity is the same. So the upper interface is at 90% of the centerline velocity, roughly in the middle between the wall and the centerline on average. And the lower one is at 80% of centerline velocity, which is a little bit closer to the wall. So we can see the interface, so the clustered vortices along the interface, it looks like the interface is persistently threading through the vertical structures. And in the azimuthal direction, so the vortices are elongated and distorted in the cross-rim plane. And we can see that interface contort to follow the vortex distortion. On the right-hand side, we plotted the average vorticity near the interface separately for prograde and retrograde vortices. And there is a peaking observed across the interface. There's a peaking of prograde vortices rather than associated with a lowering of the retrograde vortices. So this means that the interface is preferentially attached to the prograde vortices. So in this movie, we can see the attachment in time is very persistent. And the lower one here is how we applied a window that moves with the interface downstream. So we can see the local change of the interface along with the vertical structures. So we can see the interface contort to follow the inclined trains of eddies here, and they change in shapes when the local vertical structure weakens, disappears, merge, and coalesce. And this is the same in the cross-rim plane. So when the vertical structure contorts, the interface contorts with it. So now let's look back to the 3D surface of the interface colored by the elevation of the interface in the wall normal direction. So now in red are the bulks of ejections, and in red valleys are the downward sweep. So the fluctuation of the interface in wall distance around its mean value is showing above as y prime. So this interface is again roughly in the middle of the pipe center and the wall, showing no clear bias between ejections and sweeping. But we do notice that the shape of the bulks and valleys are quite different. So the upper part, the ejections are very rounded and the sweeping are quite pointy. And now if we look at another interface from the same snapshot but defined at a lower velocity threshold, being much closer to the wall, we can see a clear bias towards high ejections and bursting events. And also the shape of the ejections and the sweepings are reversed, so the ejection become very pointy and spiky compared to the flattened sweeping structures. So we measure the skewness of Y prime as zeta, which represent the imbalance between ejections and sweeps. Positive zeta means the fluctuation is skewed to ejections. The skewness to ejection is at the highest when closest to the wall in group 6 in yellow. So this asymmetry of ejection over sweeping decreases monotonically towards the pipe center, and eventually in the last group in blue, it becomes inverse. So there is a sweeping over ejection. The sweeping is stronger than ejection here in this group. When zeta is nearly 0, it means that at this location, the internal shear layers are very symmetric. So the local ejections and sweeping are nearly balanced. And we think this is a location where the large scale and small scale interaction is roughly at the balanced state on average. Another feature of the interface is the spikiness of ejection part and sweeping part. So we measure the curtices of the Y prime signals for its positive ejection parts and negative sweeping parts separately. So high curtices means the signal is very pointy. The solid line for ejection suggests that the ejection are the spikiest near the wall and smooths out with the wall distance. And the sweeping structure starting from the wall, so by the dashed line, on the other hand, are the flattest near the wall, and it gradually becomes spikier towards the pipe center and eventually becomes spikier than the ejections in the pipe center. So the spiky lower part of the spiky lower part sweeping structure of the interface away from the wall, and the spiky upper ejection part of the interface in the neural region, and with the neutral region in between, with the symmetry between ejections and sweeping. So it forms kind of a reverse structure shape between the neural ejections and the large scale sweeping from the center, like this one. So in summary, we investigated the incompressible turbulent pipe flow at ITAL 500, and the scale of the three-dimensional meandering of the interface increases towards the pipe center. The vertical structures cluster along the interfaces and is predominantly prograde vortices. The interface evolutes with the local dynamics of the vertical structures. In the neural region, there's dominant ejections over sweeps, and this imbalance restores when leaving the wall and towards a sweep over ejection state in pipe center. So the structure shape of the neural ejections and the large scale downward sweeps are reversed in the pipe. There's more details in our recent paper, and thanks for listening.
Thank you very much for your talk, Yvonne. That was very interesting. We have a couple of minutes before the end of the meeting. Is there any questions for Yvonne? No. I have one question. I don't know at what stage you are with your PhD, but are you going to investigate the influence of the Reynolds number on your for this work to investigate ejection sweeps and uniform momentum zones as a function of Reynolds number?
Oh yes, of course. We've done part of that, and we have a paper under review, but we are doing more for using all four Reynolds number we have. So from ITAL 180 to 1000. We don't have anything higher than that now.
And no, that's fine. It's just I was wondering if your conclusions are still valid when you increase or when you decrease the Reynolds number. But basically, the fact that you have more ejection close to the wall than you have sweeps.
So far, the results is kind of there is Reynolds number trends on it, definitely. But yeah, so the conclusion I just in the last slides, it holds for the Reynolds number we have.
Great. Thank you very much. There's one quick question from Oliver Buxton.
Hi, Hugh. Very nice talk. I really enjoyed it. When you choose your momentum zones, you did it based on the histogram. Could you go back to that slide? Would that be okay?
Yeah. Wait a minute. I can't really hear you clearly. Your voice is a little bit low.
Oh, sorry. Can you hear me better now?
Yeah.
A little bit better.
Okay. So basically, looking at this histogram, there seems to be well. Can you talk me through the momentum, the sort of the definition that you decide for your momentum zone between, let's say, 0.7 and 0.8? How it is that you decided that particular interface?
So yeah, so basically we have this histogram instantaneously, then we have a kind of like a peak detection scheme. So we select the peaks, and to be fair, we don't select peaks too close to each other. And then for this one, we have 3 peaks recognized, and for the recognized peaks, there's always a bin. So we always choose the bin between the 2 recognized peaks, so the minimum bin.
Okay, I'm simply looking at the one that's the furthest to the left. It seems like there may or may not be a minimum there. I wonder whether you want to comment on essentially whether you think that there's some arbitrariness in the way that you decide on these interfaces, because to me it looks like the red line that you're hovering over now looks kind of a bit dubious, I think.
Yeah, I mean, if I actually look at every histogram, it must be a few of them looks quite arbitrary, I know. But for statistics, we've tried different methods for like more without some method without user-defined threshold, like with this one. But well, the results hold the same. But yeah, so the limitation of this histogram approach is that when you have to define lots of parameters to kind of for this peak detection scheme and for the definition of the interface.
Okay, because clearly there's something going on at these interfaces. You show there's a peak in the shear rate, and you show that there's clearly a change in velocity across this interface. So I wonder whether there might be a more sophisticated method for determining where these interfaces are than this histogram, which I would say this is the least convincing argument that you presented, perhaps. Yeah.
So if you use there are some more sophisticated methods. So if you use like the calculate the tensor of rotation and so the vorticity, and you put just one threshold for the vorticity, then you kind of have these top shear layers not as a continuous line, because the only way of having continuous line enclosed is by having like a fixed velocity threshold like this one. But still you can have lots of elongated structures in the cross-rim plane. And we should see the same results later in conditional averaging.
Okay, all right, thank you.
Thanks.
Okay, great. Thank you very much to the speakers. Thank you very much all for attending these first online talks. I hope you really enjoyed it. And I hope to see you again at the beginning of December. I will try to advertise as much as possible about those talks. I think it's very interesting to see what everyone is doing within the UK Turbulence Consortium. On this note, I'm going to stop the recording.